Hello, college algebra student. This video is for chapter 6.7, exponential and log models. So we continue with exponential models where we're dealing with exponential growth. So this is so the main pro the main things that you need to be aware of if someone gives you a work problems of a exponential growth or decay, you always want to make sure that you have one of these set up. Either y equal to a0 e of kt, where k is the growth rate, continuous growth rate, or if you know doubling time, y equal to a0 2 to the power t divided by the double time. Okay, so this is the doubling time. So sometimes they tell you how long it takes for them to double, then you would use this model. Otherwise, you get that. Now, sometimes you don't have any of them. So just like in example 2, you look at this question. The count in the bacteria culture was 200 after 10 minutes. You don't know the initial. They just tell you that it's 200 after 10 minutes and 1400 after 30 minutes. So you can write any of them. It is not doubling time. It's not continuous growth rate, and it's not even initial. So they just have two instants. So this is exactly what you have long times ago when we have two instant and we have to model a exponential function. So we would actually write two instants, t equal to 10, y is 200, right? It's like a point, and t equal to 30, y is 1400. Substitute into the model that you want, which is y equal to a0 e of kt. So because of that, then the 200 is y. So you have an equation of 200 equal to a0 e to the power 10t, because t is 10k, not 10t. T is 10. And then for the other sets, you have 1400 equal to a0 e to the 30k. So with these two equations, you can solve for k and also a0. And once you solve them, then you would have your model. So it is important to figure out whatever that they give you to come up with the model. So to do this, we would solve for a0 first. So if I do divided by e of 10k, so this would be a0, right? So a0 is 200 over e of 10k, but k is unknown, right? So what you do is you plug it in here. So you would have 1400 equal to 200 over e of 10k times e of 30k. So then you would have 1400 equal to 200. You have e of 30k minus 10k, so e of 20k. When you're dividing of the same base, you can subtract them. So it's 20k. So this is one equation. And we are just going to solve for k. So divide by 200. So you would have 7 equal to e of 20k. Okay. So then you want to solve for k, you do add ln on both sides. Ln 7 equal to ln e to the power 20k. And 20k would move to the front by log property. So ln 7 is equal to 20k times ln e, which is 1, right? So k is ln 7 divided by 20, right? So put in the calculator, you can use decimal to do. ln 7 divided by 20, so 0.972955. Use as much like places as possible because you don't want to have too much rounding error. 0.0 what 972955. 972, is it 00 or 0? 97295. So this is the growth rate. It's growing 9.7 percent per minute. Per minute. This is per minute. So and then we have to what is it? The first one was the initial size. Initial size is this one, right? So this is A0 200 over. So A0 is 200 over e to the 10 times 0.0972955. So just plug it in. So that would equal to 200 divided by e to the power 0.0972955, the one that it is on the top, times 10. So 75.6. Now for bacteria number, so it should be 75.6. So you can round it to 76, but this rounding seems too much. So for the um equation, I'm just going to keep the 75.6 for the time being. So I would say the equation is y is equal to 75.6 e to the 0.0972955t. So this is the function that model the growth. Oh, what is the model doubling time? So t is, we always know doubling time is ln2 over k. We already solved for k, 0.0972955. So let's figure out how long does it take for them to double. So ln2 divide 0.0972955, 7.12. So the doubling time is 7.12. Okay. Minutes, I think. So use the exponential model to substitute. So C is what we find out. Find the population after 95 minutes. So now that you have doubling time, you also have this. You can use either way. Okay, so you can also use y equal to 75.6 2 times t over 7.12. So both of them are available for you. So you can just find out what it is. So in this case, t is 95. T is 95, right? So my y would equal to 75.6. I'm going to use the exponential model. E of 0.0972955 times 95. And that should give me the amount of the bacteria after 95 minutes. So put it in. What? 75.6? Yeah. E to the 0.0972955 times 95. Just very tedious. 781154.9. So 78, gosh, 1154.9. So it is a lot of bacteria. So you can round it to 81,155 bacteria. So D is to solve for what? To find out when will the population reach, when will this bacteria culture become 12,000? So again, you can use the same model that you have solved. So this is important that you solve it. So you would use it again and again. 12,000, is it 12,000? 12,000. Why do I write y equal to 19,000? This is a typo. 12,000. So I'll say 12,000 is what I want. And my initial is 75.6 is e to the 0.09, what, 7? Forgot what it is. 2955. 2955 times t. We don't know what time it is to get 12,000. To solve for t, clean up the 75.6. So it would be this one, do ln on both sides. Just very tedious. Ln of e of 0.0972955t. Once it is behind the e, the ln, this move to the front. So I have ln 12,000 over 75.6 is equal to 0.0972955 t times 1 times ln e, which is 1, right? So t would be this number divided by 0.0972955. So that would be equal to t. So that I put it in the calculator. 12,000 over 75.6. Okay. 12,000. Oh, no, ln of 12,000 over 75.6. And then divide k 0.0972955. So 52.08. So 52 minutes. So after 52 minutes, it should have 12,000. 52. This is the answer. Okay, example 3. Wow, takes a long time. Example 3 is, so if you don't have the continuous growth rate, or you don't have doubling time is difficult. You have to solve for it. And after you solve for it, sometimes you round it to a very funky number. So when you solve these, it's harder. Okay. So hopefully we don't have to do a lot of those. Example 3 is, this is good. A population of bacteria double every 40 minutes. So you can write the equation really fast. Y equal to, initial count is even given, 602 times, what's the doubling times? 40. So you say small t, which is what the time you're supposed to plug in, divided by 40. That's the exponential equation that will represent the population at time t. What is the population after 70 minutes? So you just plug it in. Y equal to 600 times 2, 70 over 40. So that means 600 times 2 to the power 7 over 4. So put in the calculator. Delete all this first. 600 times 2 to the power 7 over 4. So 2018, if you round it to a whole number, bacteria. Okay, so that's easier. And the fourth application is, of course, exponential growth can be used to model money growth. If you know the continuous compound interest, in this case, it's 5.5%. Initial deposit is 32,000, so this is very good. You have the initial number and you have K. Continuous rate is the number that you can use to write the amount that would be in the account. Right? So the amount in the account we know is A is equal to P e to the RT, right? This is R is just the K. So in this case, so it would be, what was it, 3,200? E to the 0.055 T. So that's kind of our basic model. Let's look at it, if it is the right. Oops, too much. Okay, 3,200, 5.5. Yeah, that's right. So then if you want to find the amount after 18 years, so A or Y would equal to 3,200 E of 0.055 times 18. So it's just a matter of putting in the calculator. So delete this. So 3,200 times E to the power 0.055 times 18. 8611.95. So you would, after 18 years, is like almost triple, right? How long does it take for it to double? Oh, that doubling time is ln2